let you know. Okay.
Yeah, sure.
So, okay, the first speaker is Swati from University of South Carolina, and she will talk about congruence module, high powers for class and partition functions. Swati, please take over.
Yeah, thank you for the introduction. And I'd like to start by thanking the organizers for giving me the opportunity to present my work. So I'll be talking about congruences modulo prime powers for a class of partition functions. It is a joint work with Matthew Boylan, who's my PhD advisor. So a quick overview, I'll start with motivation and then followed by some background, and then we'll move on to main results, examples, and at the end, I'll give sketch of my proofs. So we start with discussing the usual partition function. So a partition of a non-negative integer n is a non-increasing sequence of positive integers whose sum is n. P of n basically counts the number of partitions of n, with P of 0 defined to be 1. As an example, we can see that there are 5 ways of expressing 4 as a sum of positive integers. So basically, P of 4 is 5. Now, moving on to some important results in the study of congruences. In 1919, Ramanujan showed that for a non-negative integer, we basically have partition congruences of this form, and they hold for these triples, and they do extend to prime power moduli as well. In 2000, a surprising result of Ono basically shows that if we take this A to be non-prime power, then we actually have a positive proportion of primes such that this occurs. So basically, we have infinitely many Ramanujan type congruences. Now, the first motivation for our result basically comes from the work of Ahlgren and Boylan. In 2003, they showed that if we take L to be a prime greater than or equal to 5 and J to be a positive integer, then we can identify this generating function for P of n in this arithmetic progression as a modular form of weight 1/2. And they do specify these parameters R and K depending upon the parity of J. Now, another result where our motivation comes from is the work of Yang, which basically addressed the question of finding like more congruences of the type that we just saw in Ono's work. So what he showed is that if we take L and M to be distinct primes with L bigger than equal to L greater than equal to 13 and M at least 5 and J to be a positive integer, then like there exists this explicitly computable integer k such that you can get every congruence of this type modulo L. So basically, it addresses the algorithmic aspects of finding congruences which occurred in the Ono's type. So moving on to the framework of our work, we consider this partition function P1 P of n for any prime P, and the generating function is given by this infinite product. Now, the reason why it is interesting is it counts the number of partition pairs such that the sum of their parts is n, where we have a restriction on beta that it consists of only of parts that are multiples of P. So what we prove is we firstly give an analog of Ahlgren-Boylan's result for this partition function, and we also provide the analog of Yang's result for this partition function. And I'll also describe some explicit examples that basically illustrate our theorems. So before I move on to the statements of the theorems, I'd like to give some background of what is a modular form. So it is a holomorphic function on the upper half plane, and we call f to be modular of weight k if for all gamma in SL2Z, we have this modularity condition, and this k is basically the weight. Like we also call this automorphic condition. It does extends to half integer weights, multiplier systems, etc. Another thing we have is the growth condition at the cusps. So if f is linear exponential growth at cusps, we call it weakly holomorphic. In simpler terms, you can basically say that F is allowed to have pole at cusps. And if it is bounded at cusps, so it is called holomorphic modular form of weight k. N is the level and chi is the character mod n. And similarly, if it vanishes at cusps, we basically call it a cusp form. And you can also treat this holomorphic condition as bounded at cusps. Basically, if we are taking the Q series expansion, so the indices have to be like n has to be greater than equal to 0 and so on. And vanishes at cusp means the constant term is 0. Now, one of the main examples of modular forms comes from the family of eta quotients. And in general, an eta quotient is a function of this form, basically given by this infinite product where delta and r delta are integers and delta is basically positive integer. Now, one important result is if we are considering an eta quotient, then there is an explicit formula which will give you the order of vanishing at any cusp of the eta quotient. And this h is basically the width of the cusp. Now, moving on, we talk about operators on modular forms. So there are two important operators that I'll discuss. Which now starting with the Heck operator. So Heck operator, they are basically linear operators on spaces of modular forms of which, so they basically preserve the space of modular forms as well as the cusp form given by this sum. And this is this V, by that I mean the V operator with the and similarly, this is the U operator. Now, one important family of operators that we use in our work is the trace operator, which basically is important in our case due to the level lowering phenomena. So if we take L to be a prime, N to be a positive integer, and L exactly divides N, so trace operator is gonna take the modular form of weight k level N, and it will drop the level by a factor of L. So it will take N to N over L, and given by this form, where this WLN basically represents the Aitken-Lehner involution. Now, something to note is that if I relax this condition and say L square also divides then we have U operator, which plays a part of level lowering. So moving on to the first result. So if we take L and P to be distinct primes with L at least 5 and J to be a positive integer, then we can identify the generating function for our partition function P1P, which lying in this arithmetic progression as an eta quotient times a holomorphic modular form of weight k level P with integer coefficients, and that holds modulo any prime power. Now, something to note is that the right-hand side of the congruence, it is weakly holomorphic in general. And our theorem makes all these parameters x, y, and k to be explicit. Now, if we take p plus 1 divides 24, then the right-hand side actually becomes holomorphic. So, y is greater than 0. And the weight k in this case, when p plus 1 divides 24, is actually minimal. So, and we also identified that this generating function lies in this space, which is consisting of multiples of eta quotient times holomorphic modular form. Now, we'll see some of the reasons why this space is important. So, firstly, one of the major things is that this space lies in the dimension of this space is much smaller compared to the ambient space in which it lies. Here you can see that it is isomorphic to modular forms of weight k level P, whereas the space in which it lies has much bigger dimension. And Another important result is that in a recent work, Boylan and Warnock showed that if we take P and M to be distinct primes with P to be in this range and M at least 5, then this space is actually invariant under the Hecke algebra. And something like one more thing to keep in mind is like Tm square, I mean integer weight Hecke operators. And their result is much more general, holds for other values of the what do you call P, or holds for other values of level as well. Now, as I mentioned that we do have explicit values of all the parameters in our case. Now, something to focus in this table is that if we take this P plus 1 divides 24, then we do have the exponent to be greater than 0. So we do land up in holomorphic spaces, whereas in other cases, it is negative or I mean 0, which is not that interesting. And then moving on for even j, we see the similar phenomena that only in the case p plus 1 divides 24, it is greater than 0, and otherwise it is less than or equal to 0, the exponent y, which occurred in the eta quotient. And then we have k to be minimal in this case when p plus 1 divides 24. All right, so I'll try to illustrate it by means of an example. So let's take the case of odd j, p to be 5. Now, because the dimension of modular forms of weight for level 5 is 3, so we consider these basis elements. So if we take L to be in this range, then we have the generating function of partition function P1 5 of n is isomorphic to this eta quotient times holomorphic modular form, whose like if we the weight is of course given by this, and this is the exponent y, and you can explicitly identify how this form looks like in different values for different values of L, K, and Y, and the pattern repeats. Like if I even take L to be further 23 and 29 and so on, so Y will keep switching between 1 and 3. But yeah, the point is that we do know the explicit forms of HZ in each of the cases. Moving on to our next result, we prove the analog of Yang's result for the partition function P1 P of n. So we take L and P to be distinct primes with M and P in this range and J to be a positive integer. So what we show is that there exist these explicitly computable integers J and N such that you can get congruences, infinitely many congruences of this form, modulo any prime power. And this D that you see here is basically the denominator of theta quotient. And similarly, we do have congruences of this form as well for all non-negative integers W and N. Again, this holds modulo any prime power. Again, let's try to understand it by means of an example. So in this case, we take J to be an even integer and PLM to be distinct primes. Now, the space of modular forms of weight 6, level 3 is 3-dimensional. So we take these bases. So by our first result, we say that the generating function for this partition function, the denominator is 6 in this case, the D that I was talking about. So it is isomorphic to this eta quotient times a holomorphic modular form, and it lands up in this space. Now, the dimension of this space, as I mentioned before, is same as the dimension of modular forms of this, where this HZ lands up. So modular forms of weight 36 and level 3, which is 13. Now in actual, if I don't consider this isomorphic phenomena, so it actually lands up in a space of dimension 120. Like it lies in a space of modular forms whose dimension is 126. but because we already said we prove that it is isomorphic to the modular forms of weight k, so we land up in a smaller dimension, which is 13. And so let us consider these 13 basis elements. Again, we do identify them as eta quotient times a holomorphic modular form. Now, by this result of Bolen and Warnock, because this space is invariant under the Haka algebra, so we do say that there exists M such that the following identity holds. And this is how the matrix M looks like modulo 49. So this is basically encoding the action of uh, the Heck operators Tm square on the basis of the space, on the basis of the space A53. Now, this is the matrix which gives a rise to, which basically like where this order J comes from. So if once we get the matrix M, so we build up this matrix, and this explicitly computable integers J and N that I was talking about, they basically come as orders of this matrices in PGL2D C mod 49C. So in this case, we get J to be 1176. And if so, that basically gives us the first congruence that we talked about. And similarly, if we consider the order of this matrix in GL2D, Z mod 49Z, that gives us our another integer n. So which gives us our second family of congruences, modulo 49. So basically, once we get this matrix A, we just need to check the orders in PGL2D and GL2D, and that will give us G and N respectively. So I'd like to discuss the main ideas which went into the first result. So again, we are in the setting that L and P are distinct primes with L at least 5 and J to be a positive integer. So we consider this modular form of weight Lj minus 1 over 2 level Lj, that's the character. We take into account another modular form of, again, this weight level L and character chi mod L. Now, if we look at the product acted upon by ULJ, we do get this infinite series times this infinite sum. So from this series, it is not hard to observe that the order of vanishing at infinity for this form is basically beta plus delta over Lj. And on a similar terms, we can also, by some work, we can also show that the order of vanishing at the other cusp 0 is also gonna be beta plus delta over Lj. Now, one important lemma, like like if we assume the truth of this lemma, then our theorem follows. So if we take lambda to be this integer, then there exists this modular form of weight lambda level p with integer coefficients such that the product that we discussed acted upon by ULJ is isomorphic to GZ mod LJ. Now, how this modular form GZ comes into picture, or how we are getting it is like if you just look at this inner parenthesis, so this is a modular form of weight lambda level LJP. We act this by the operator ULJ minus 1, which will drop the level by a factor of LJ minus 1. So that leaves us with modular form of weight lambda and level LP. And if we like the reason this WLPL is shown is because we need more and more powers of L so that we can get the L-adic valuation to be at least J. But once we land up in the space of modular forms of weight lambda level LP. Then once we apply the trace operator, so it will knock off the level by this from LP to P. So we basically get rid of this last L with the help of the trace operator. So as I mentioned, we are using these U and trace operators, which are both helpful in level lowering depending upon what power of L is dividing the level. So this is how GZ comes into picture. And once we assume that this is true, some more work will basically show that our first theorem holds. Now I'll give a brief sketch of our second result, of our second result. So we are in this setting that L and P are distinct primes with L and 5 and L and M in this range and P to be 2, 3, 5. So we suppose dimension of the space to be D, which is same as the dimension of modular forms of weight K and level chi, and we take these D basis elements. So an important result, which is helpful in proving our second theorem, is that for any positive integer I, there exists these Mi, Ni, Oi, which are D by D matrices with integer entries such that you get this 3-term recurrence relation with Mi satisfying this property, and A is the matrix which basically gives result to this integers J and N that arise as order of these matrices in PGL2D and GL2D. Now, this 3-term recurrence relation that I talked about, the first component is like if I just look at the case I is equal to 1, so the first component is coming because of the Hecke invariance of the space. And then, of course, it follows from the definition of Hecke operators as well. And then once you keep iterating it, you'll sort of get this first term, which is coming from the Hecke operator, the twist term, and something associated to the V operator. So once you have this matrix, J and N will be there, and that will give result to the family of congruences for the partition function. That's it. Thank you.
Schedule 5 minutes later, so we are okay to take some questions. So any questions? Yes. We need to let her know. Let her. Oh, thank you. Thank you.
Sorry, I shouldn't have sat here. Yeah. Okay, I just had a question on slide 10. There was a x in the exponent of q. I wanted to know what that relied on, or yeah, q to the n plus x, yeah.
Okay, so need to remember that beta plus delta over Lj. So if I have to give the explicit value of x, it is basically beta plus delta over Lj minus Lj p plus 1 over 24.
Okay. Thank you.
Okay, thank you, Swati.
Yeah, thank you.
Let's thank the speaker again.